Oh, the fun forces. So when you get to this point in your introductory physics, you're gonna have quite a bit on your hands to be able to understand all of these different forces and then how to tackle them. Now, don't get frustrated in any way. Forces are definitely something that we experience on a continuous basis. We can't really move around without them. So it is worth our time to try to learn about them. So I just want to introduce this concept here, and it is meant for students that are most likely in around grade 11 starting physics or possibly taking an introductory physics course. So forces falls into basically the chapter on dynamics. Now, you have studied kinematics, and kinematics in the beginning is basically nothing else but the concept and study of how things are moving around. So what is their position? What's their velocity or speed? What's their acceleration? And that is all about kinetics. But, the question that we would like to ask is, why do objects actually move? And if you ask that question of why and what is actually a cause of this particular movement or a prevention of the movement, well, that has something to do with this new physical quantity, which is force. And as soon as you're asking, why objects are moving, then you are studying dynamics. So welcome to dynamics and welcome to forces. And so here is a little bit of an overview of what forces are, and I'll try to give you kind of a little bit of a step and a back step as well, of where you're going. So forces, or force, is a physical quantity. We designate it typically for capital F, and we do certainly we'll put the vector up above there, so that symbol. Although if anyone writes force just as F, and sometimes I do that because I get lazy and I don't want to write that little vector. So if you do see a force, do always keep in mind that it is a vector. So it's a physical quantity, it is a vector. Now, what exactly is it? Well, if it has something to do with causing movement or preventing movement, then it actually is something related to either a push or a pull. And these pushes and pulls, for us, especially in the beginning, it's actually enough to understand, if you're pushing something or if you're going to be pulling something, you can imagine that, that is actually a physical quantity. And of course, it's a vector because you have a direction. So you're pushing in a certain direction, and then you're pulling possibly in a certain direction. So that's all that I want you to think about, especially in the beginning with regards to these forces, right? So it's some kind of a push, some kind of a pull. Sometimes, they're magical, and we don't necessarily have to apply it, to be able to see movement. But that is, the phenomena that happens, in nature. So this particular push or pull, so I've just kind of mentioned, has something to do with possibly trying to change, the motion of an object, or possibly, it might be preventing the motion of an object in some particular way. And these pushes or pulls, they are actually doing that in some way, and we have to kind of break them down. Now, the unit, is a new unit. So, as you've kind of stepped yourself through, so starting off with distances, right, or possibly positions, you basically looked at the SI unit, so the standard international unit, and the standard was really meters for that. You kind of shifted over, started talking about speed and velocities, and you've noticed that it was meters per second. Sure, we can have all kinds of other units, but meters per second was our actual standard. And then if you wanted to accelerate, you've noticed that you had meters per second, per every second. So how was actually velocity changing with respect to time? And that came about with meters per second squared. So you have seen that, right? So this progression through. Now, if you think back of the foundational physical quantities, so kind of the core base quantities, there were three. You had distance, you had time, and both of these interacted to create for you now positions, displacements, velocities, speeds, accelerations, right? So it was some combination of those two, okay? Some kind of a distance, okay? Some kind of a time. But the third one was mass. And notice that you didn't actually talk about mass at all, or you didn't even use mass at all when you were studying kinematics. It was kind of independent of mass. And that reason for that was basically because we neglected all kind of resistances. Now, a resistance is actually some kind of a force, all right? And it's actually a frictional force that we have. Now, that third mass, once you integrate it, right? Now that you're interested in why is this motion happening or why is it not happening? Well, it is dependent on the object, and the object itself will have some kind of a mass because it's going to be made up of matter. So once you introduce that, you can talk about the new unit, and the unit, okay, is named after Newton, and Sir Isaac Newton has probably done the most work, okay, on forces, and in particular for this chapter. And so in his name, we use the unit of newtons. But if you take a closer look and break down what a newton, this capital N that you see here, what it actually is, it's nothing else but kilograms, okay, notice, multiplied by meters and divided by seconds squared. Now, if you remove kilograms altogether, and you only concentrate on meters per second squared, and you think back of what that actually was a unit for, hint, acceleration, now you start thinking about, well, acceleration is changing movement, right? And kilogram was the actual unit that we had used, okay, with regards to mass. So gram is typically one of the base units, but the standard SI units for mass is the kilogram. And so once you combine these, okay, you can create this Newton. Now, as you keep going, okay, I will actually kind of come back to this once we take a look at few of the Newton's laws. And I'm going to come back to you and let you know, all right, what did this Newton actually come out from? But for the moment, you have to kind of assume, okay, that the unit that you will use will be newtons, and it really is kilograms times meters divided by seconds squared, which isn't really very convenient to be able to write. So it's much more convenient to use newtons, and that's what we will use. Now, it's not the only actual unit. The same thing as we don't just have, for example, meters for distances or positions. We can have it in feet, right? We can have it in kilometers. We can have it, okay, in inches and centimeters, all kinds of different things. For forces, you typically will run into basically two different types of unit. The standard unit, which is Newton, and then you can put a prefix in front of it. So you can certainly say, okay, you know, kilonewtons, for example. So that's with a prefix. But, okay, not in the metric standards, but you can use it in the imperial standards. And that is something that you are used to, and we use pounds. So pounds actually is something to do with forces, all right? So you're going to be running into that, okay, as you're going through. So that's all I'm going to say for the moment with regards to these forces. So it's a push or a pull of some kind. You can imagine pushing the door open, you know, you can imagine pushing a box, okay? You can imagine, you know, pushing against the wall, although I don't think, you know, we're that strong to be able to move it, but we can certainly imagine these actual pushes. And then we can imagine pulls, right, as we're pulling things along, okay? And all of these, what are they trying to do? They're trying to change motion in some way. So now, there are several key types of forces, okay, that you should be aware of, and I want you to watch out for as you're going to be doing, okay, these things and studying them. So here are just a few. These are not all the different forces, but typically on the introductory side, these are the ones that you will run into. So there's a force of gravity, right? So that one will make a little bit sense to you because you've already talked about in kinematics the acceleration due to gravity. So gravity, the Earth is actually pulling us, okay, in some way. Notice the word pull. So it's like attracting us towards itself. And we mention anything to do with a pull as a force. So that particular force, and it's caused by, okay, the pull from the earth, okay, and we call that force of gravity. Now it's magical because if you jump up, it starts to pull you down, and it's not like you can see that something's attached to you and it's pulling you by a rope of some kind, but we do observe it. We clearly do see it. So there is a pull that happens. Now the other, which is basically very analogous to gravity, I mean not necessarily analogous, but it goes hands in hand with gravity, and that is the normal force. So anytime you have an object, and you can imagine, at least for the moment, I would want you to imagine that you have some kind of an object, and let's say maybe it's standing on a table, and this particular object, and I'm going to just draw a ball and make that object a ball. So if this table is strong enough, right, you will have some kind of a pull, and this would have been the force, okay, that we would have with respect to gravity. So try to pull it down. And that particular force, okay, that we have, very often with regards to objects, we call it their weight. So that force of gravity, or the weight that we have, it's that pull. But if the table is strong enough, well, then it's not necessarily going to go, okay, and break the table through. That table must be doing something, okay, and it will relate it back to Newton's one of the laws. And what we find is, well, this ball isn't really falling down, it's just kind of standing. Now if I remove it, of course it will fall, but for the moment, okay, there is this sense between the actual table, okay, and the ball itself, you know, right at the point where they're actually meeting, something is happening there that is preventing it. Because if this was the only force, this would just kind of fall right through the table, but it doesn't. So there has to be some other force, okay, that is acting in the opposite direction. And that force, very often we call this the normal force, okay? So that's how you will see it and abbreviate it with a little n or a capital N, okay, depending on who is writing it. I use both, capital or lowercase n. So you have this actual normal force, and it's in the opposite direction, notice, okay, than the actual force of gravity. It doesn't mean that both of these are always going to be the same, right? So that actually depends on what's happening with the object. But there is always this normal force which is acting there on you. And it acts on any object, right? Now, as soon as I would remove this actual table, so if I would remove this altogether, now all of a sudden, you know, this actual force would just disappear. And then what would happen is this object would have been falling right down. Now, eventually it might then fall, and maybe somewhere down the line, you know, it keeps falling, and then there's maybe the earth itself there. And eventually, okay, it will hit this, now assuming it's not going to break or anything. And then, you know, it stands still for the moment. Well, and now that normal force returns back, okay? So that particular force now returns back, and again, because it's not falling through the ground now. So you will see this abbreviation of the normal force, and it basically acts on any object. That can be even on an object on a ramp or anything of that nature. Now, the next one is much easier to understand, and that is the applied forces, okay, that we actually put on objects. So if you're literally going to put your hands on an object, let's say on a box, and you push it, well, then you're applying a push, a force, right? Or if you take the actual box and you start pulling it, okay, well, then you're applying an actual force. So those are applied forces that we directly put on objects. And very often you might see them abbreviated in textbooks and elsewhere, just with a little a. But to be honest with you, you can drop all the subscripts altogether so long as you know that you have those forces that are applied. So that's an applied force, so some kind of a push or a pull that you or something else, maybe a robot, okay, or some other nature is actually applying this force. Now, the next force, which is the tension force, this one is interesting. So tension force is typically some kind of a transitional force. So what happens is, okay, in tension forces, and you can imagine again, so if we do have an object, and now I will put a box in here, and this particular box, let's say if it's standing on the ground, okay, and now you have some kind of a rope, right? So this rope is, okay, attached, And now you yourself, okay, maybe you're standing here and now you're going to be pulling through this rope. So let's, imagine that we're standing here and, now we're starting to try to pull this along. Well, what's going to happen is, we are pulling, right? We're not directly attached to the object, but we're pulling it through this median. And basically, maybe it's some kind of a rope, okay, that we have. And what happens is that this particular pull that we have as we're pulling along, it creates a tension here, okay? And you have this tension, okay, as it goes through. So it is a force of tension, which is applied. Okay? And it's going to pull this along, of course, if it's strong enough, okay, to overcome, okay, whatever force that we need to make this object move. That would have been a tension force. So it's kind of transitioning through an object. It doesn't have to be a rope, by the way. If you are just hanging, let's say if you're just hanging around and you're gripping something, well, then there's tension in your forearms and it goes through your bones and your muscles. And of course, they have to be able to, because the earth's trying to pull you down if you're hanging. So, right, so it tries to pull you down. And then there's tension, which is created, okay, within your arms. Okay, so now the median is actually, maybe your arms, your muscles, okay, your tendons, and so on. So all of these things are actually tension forces. Now, tension forces are always some kind of a pull, right? Because we can't really push through things. Now, there's other forces, okay? So in terms of pushes, but I don't want to go that far yet, right? These ones I want you to be able to understand. Now, the last one here is a frictional force. So frictional forces might cause a lot of scratching on your head here because frictional forces are strange. They both aid us, so they help us to move, but they also restrict motion at the same time. It's just different types of actual frictional forces. So if you can imagine if we are actually trying to pull on a rope and this box is maybe standing on some rough ground, it would be very difficult to try to pull it. Now, if it was on some kind of an ice, maybe, very low friction, right? So there isn't a lot of things that is happening between the actual surface, okay, of this box and then maybe the actual ground itself that it's sitting on right there. So that might take a lot of pulling to try to get it to start. And you might imagine that, well, as you're pulling along, well, then there is something happening in between the actual contact here between the box and the actual ground that is really resisting the actual pull, and it's trying to keep the box kind of steady there. And that would have been, the actual force of friction that is actually trying to resist that motion. Now, if you were actually thinking, and maybe let's say you're walking along, so when we're walking, we're actually using friction to propel ourselves forward. We wouldn't really want to be able to walk on ice or something which is, very slippery in some way, because we wouldn't be able to catch that grip. What we call that grip, okay, between an object, so like our foot, okay, or maybe the sole of our foot and the ground, we need that grip, okay, so that it kind of doesn't allow our actual foot to slip away. We want it to be able to actually have it grip enough so that we can push off, right? And it doesn't slip off. And that is actually friction, right? That we are using. So now friction is going to be used in many different ways. Now for us, you can think about friction, something that actually is trying to prevent motion in some way. And there are many different forms of friction. So between literally touching surfaces, but there's also friction caused by air, which might be a resistance as you're kind of moving along. There's little particles hitting you. So we also hit and refer to that as some kind of a friction as well, right? It's trying to slow you down or it's trying to prevent you in some way in terms of moving. So these are very common ones, and you're going to be running into these, okay, as you're going along and studying forces in your first chapter. So force of gravity, you're going to talk about the normal force, okay, applied forces, so direct pushes or pulls, tension, okay, so through some kind of a rope or some other item, okay, and friction. So those are the key ones that you're going to be running into. So that's the introduction that I have for you with regards to these particular forces. And I definitely do want you to think about, okay, forces in terms of some kind of a push or pull. It is related to why objects are actually trying to move or maybe being prevented from moving in some way. It is a vector, so direction does matter on your push or your pull. Okay, it's definitely some kind of a quantity. We can certainly measure it, and you'll see that we can do those measurements. And it is trying to either change or maybe prevent motion in some way. And now you've learned a new unit, okay? And that would be newtons. Although you certainly can also have pounds, and that's lbs, or sometimes just lb for pound. Okay, s is the plural. All right, so thanks for watching. We'll see you in another video, possibly on forces or something else. Take care of yourself.